additional questions, then I will do the last act. So this is just for fun. This was the first lecture, essentially, of my undergraduate quantum mechanics course, Abridged, which I think is a fun kind of toy example. Okay, so that was a lot of formalism, a lot of stuff that is very abstract. So now I want to come back to Greg's question from the beginning and say, why would you ever assume the state of a physical system is an element of a Hilbert space? That's a weird thing to assume. So I want to show you some things, some facts that are observed in the lab, which this machinery was invented to explain, essentially. So what are the experiments? Well, these experiments involved electrons which have spin, which I've been talking about. But I haven't properly explained what spin is for you, and to do so would take us somewhat far afield. Spin is associated with certain representations under the Lorentz group, which I don't want to explain properly. So rather than continuing to say spin more than I already have and having everyone pretend to understand what I mean, I'm going to do something different where I just abstract away the properties of spin. I'm not going to say the word spin, and I'm going to put different words in as placeholders, just to abstract away all of the details. So those words are going to be color and hardness. Now, the footnote says, okay, these, of course, are not real. A real electron does not have something called color or hardness. Again, these are just placeholders, which simplify the discussion, so I don't need to put in distracting detail. So let's just pretend electrons have color and hardness to make this easier. So if you buy that, if you will humor me, let me state some facts. If you believe an electron has color, the first fact is that the electron color can only be black or white. People have measured it over and over. They've always only ever gotten black or white. People have measured the hardness of electrons many times, and they've only ever gotten two results. It's either hard or soft. There's only two possibilities for each, and that's it. It's always one or the other, and it's never anything else. Now, we can observe the color or hardness of an electron by putting it into a box. So we have color boxes, and we have hardness boxes. So the way we perform a measurement is I put a screen here and a screen here. The screen will ding if an electron hits it, and I feed an electron into a color box. And if I hear a ding at the top screen, I know the electron was black. If I hear a ding at the right screen, I know it was white. And similarly for a hardness box. Feed it in, I either get a ding at the top if it's hard, or a ding on the right if it's soft. That's it. That's our idealized abstracted experiment. So how does this work? Well, I'll state a result of an experiment for you. Suppose we do the following experiment where I first feed electrons into a color box. The white ones go out this way, the black ones go towards the top, and then I feed the output stream of the color box, or the first color box, into a second color box. And I put a screen here and a screen here. It is empirically observed that if I do this experiment, every time I feed in an electron, the sound dings at the top and not on the right. So I get a ding here. So that means that if I measure a property twice in succession, I get the same result, right? It means black and then black, it's always black. I never measure black and then get white. Okay, that's comforting. What else? In this case, the two properties are uncorrelated. So if I instead do an experiment where I feed in electrons to a hardness box, I take the hard stream and feed that into a color box, and then I put a screen here and a screen here like before, the screen dings half the time at the top and half the time on the right. So that means that a hard electron is uncorrelated with its color. A hard electron will be black half of the time and white half of the time. Uncorrelated properties. So here's a question. I'll pause, and you can either answer this question using the classical intuition or using, if you are able to match this onto what we said in the previous act, using the quantum intuition, either way. But let's consider the following experiment. I put 3 boxes in a row. I feed in electrons. I take the black stream, and I feed that into a hardness box. The hardness box outputs hard electrons at the top. So I take the hard electrons and put them back into a color box, and then I put a screen here and a screen here. So my question is, what percentage of the time do you expect the final screen to ding white, and what percentage of the time do you expect the final screen to ding black in this setup? Maybe I should check the chat in case people are answering there. Black 100% and white 0%. Okay. Good. So that's the classical intuition. I mean, Odium is kind of jumping the gun and saying Stern-Gerlach. This is exactly an abstraction of something called the Stern-Gerlach experiment, which people may or may not be familiar with. Okay, so you may expect, as Holo was saying, that since I first feed this into a color box and then I take all of the black output of the color box and then feed that into a hardness box, that all of the electrons at this stage, they have now been measured both to be black, because they came out of the black port, and to be hard. So these are BBEs, big black electrons. They are black and hard. So you might think that it's 100% black. However, empirically, that is not what we find. So when we perform this experiment, you find at the end, the electrons are 50% black and 50% white. Now, this seems very strange, because we kept only black electrons. So it seems that at the end, the electrons have somehow morphed, and some of them have become white, even though all of the ones that came out of the first color box were black, right? So this is confusing. Half of the electrons exit the final box as black and half as white, even though we previously measured all of the input electrons as black. It's 50-50. Okay, that's a little weird. Let's try to probe this a little more deeply. So we'll make this more complicated by introducing more ingredients. So we have mirrors. A mirror is something that just redirects the stream of electrons. So here, there's a mirror, it bounces off the mirror and then goes to the right. And here at the bottom, there's a mirror, it bounces off the mirror and goes up. So mirrors just let us move around the electron streams. It doesn't change the hardness or color. And there's a combiner box. A combiner box just takes in two input streams. It merges the streams into a single stream, but again, does not change anything. Does not change color, does not change hardness. It just combines them into a single stream. Okay, here are 3 experiments. So in the first experiment, I feed in white electrons to a hardness box, take the hard guys off a mirror into a combiner box, take the soft guys off a mirror into a combiner box, and then they combine and go into a hardness box. So what percentages do we expect in this example? What percentage will be hard and what percentage will be soft? Think for a moment and I'll look at the chat. Holo's typing again, but I think I've traumatized Holo from the previous example, so he may doubt himself in making this guess, but let's see. It's exactly as I predicted. He wants to say 50-50, but he's not sure. Okay, I traumatized him, which is unfortunate, but okay, well, now I'm trolling, so I'm going to reverse the previous trauma. In this case, it is 50-50. So, indeed, you do this experiment. So you take the hard and the soft, combine them, and then measure, and it's half hard and half soft. So this seems to make sense, because I put in the white. You expect the white to be half hard, half soft, and then combining and measuring the hardness again didn't change anything. Okay, here's another example. What happens here? We send in hard electrons, all hard. Then I have a hardness port with a mirror and a soft port with a mirror. I combine them again and then measure color. Okay, I won't ask in the chat for this one, but I will for the next one. This one I'll just tell you the answer. This one is as expected. So you expect that I feed in hard electrons, so all of them take the top path, right? All of them come out the top and then go to the combiner box, and that means all hard electrons are going into the color box. And we know if we feed hard electrons into a color box, they come out 50-50. So here I'm telling you the answer. The result for this one is also 50-50. You get half black, half white, because all of the inputs were hard. Okay, last one, and I'll ask you for this one, and then after that, I'll stop torturing you. So, final question. I send white electrons into a hardness box. Now, the hard ones come up off the mirror into the combiner. The soft ones go down off the mirror into the combiner. Combine the streams. So now I have a combined stream of hard and soft electrons going into a color box. And remember, hard electrons are half white and half black. Soft electrons are half white and half black. So what percentages do I get in this one? So when I measure the color of the combined stream, what percentage is black and what percentage is white? Oh, I have a ping. Yes, I did say that. So we have a collection. K-star has been assuming we start with 50-50 for both properties. Well, in this case, we're starting with all white in this experiment. So all of the input ones here are white. So the ones going in the beginning are 100% white, 0% black. But in some experiments, we had uncorrelated ones or random ones. So it's somehow going to be 50-50. I'd say 100 to 0. Okay, so we have multiple guesses, it looks like. Actually, I'm out of coffee, so this is a good point. Actually, I'll let you discuss for 2 minutes. I'm going to go refill my coffee and let you discuss in the chat, and then I'll leave the experiment up and then see what the consensus is when I get back. So give me 1 minute. Okay, I have returned. Let's see. Maybe I'm trolling. Explain. What is wrong with that? Greg's reasoning is 50-50. Looks like Arduinin is also thinking 50-50. And OTM, although OTM claims that my 64-slide talk has 10 slides of content, which I emphatically disagree with, he seems to have not made a prediction. Oh, no, he did make a prediction at the beginning. He said, he said 50-50 somewhere, right?
He said yes when I said 50-50.
Okay. Good. Okay. Any other comments, or does anyone want to explain reasoning before I reveal the answer, or are you eager to hear what happens?
Maybe because when they all took the up path, and they just it came up 50-50. So when I take the two paths, maybe it like cancels out and goes to 100% one color. I don't know.
Yeah. Okay. That is a possibility. Good. So, wait. There was another question. K-star said if color is unrelated with hardness. Yeah, that was a result of a previous experiment. So we saw in this experiment that even though color is unrelated to hardness, you could. Where was the beginning one? You could take black electrons, get 100% black coming out, measure hardness, and then get 50% black, 50% white. So we already saw in a previous example, you can take 100% of one color, do successive measurements, and then get 50-50. That's possible. When I said color is uncorrelated with hardness, the precise statement of that sentence is just this slide. if I only measure hardness and then measure color, I get 50-50. This is what I meant by uncorrelated. So this is true. In this case, you measure black, hard, and then get 50-50. So it's uncorrelated in the sense of this slide, not in the sense that you're thinking of, I think. Okay. Probably something to do with how the words color and hardness are formal. No, it's actually not formal trickery. So I'm not hiding anything. It does have to do with spin, but this, in fact, has nothing to do with spin specifically. For any pair of non-commuting observables, as they're called, the exact same results of this experiment would come out the same way. So it's actually not that much formal trickery. It's just the color and hardness, I think, make it easier to talk about. This is a universal fact for any non-commuting observables. Okay, so there were several predictions. There was 50-50. There was Killer's suggestion that it's going to be 100% for one of them. There was various confusions, which is good because it's very confusing. So let me now tell you the answer. When you do mirror experiment 3, you get 100% white and 0% black. This is something even people who have learned quantum mechanics before will sometimes get wrong. People who have taken quantum mechanics will look at this and say, oh, it's 50-50 because you collapse the wave functions both here and they're both collapsed to hard and soft. Hard and soft are each 50-50. That is wrong. The output of this experiment is 100% white. This is extremely confusing and significant. So let me dig into this a little more. And I promise I'm almost done. I started 5 minutes after, so I'm now at 2 hours, but I will stop after this explaining this, because this is the big punchline. Why is it 100% white, 0% black? Well, before telling you why, let me rule out some of the possibilities you might be thinking of. First, you might be thinking, oh, well, okay, can we figure out which of these two paths the electron took? Because I know the electrons that took the top path were hard, and the hard electrons are 50-50. And I know the electrons that took this path are soft, and soft ones are 50-50. So let me figure out which path the electron took. Let me put in a wall. So I repeat this experiment where I put in a wall at the first step. So after the hardness box, I put in this wall and none of this part happens. If I repeat the experiment with the wall, then instead of getting 100% white and 0% black, now I get 50-50. So I put in the wall and it changes the result. I get 50 white, 50 black. Let me do it the other way. So let me put in a wall here and repeat the experiment. So this path is not accessible. I put in a wall, the electrons all take the soft path, and now I get 50-50. I take away the wall, allow them to go through both paths, I get 100% white, 0% black. What if I put in both walls? Maybe you think, oh, something confusing is happening here. Surely some of the electrons are going out along some different path and not hitting either of those mirrors and trolling me. No. Suppose I put in a wall here and a wall here. Both paths are blocked. Now I get 0% both. Nothing happens. So if I block both paths, I get 0 electrons at the end. So let's be a philosopher for a moment and attempt to use words to understand this. What logical possibility happened in this experiment? Well, let's try to ask a set of mutually exclusive questions. One of the following 4 possibilities must be true. Did the electron take the hard path? Well, no, because when I put in a wall in front of the soft path, when all of the electrons took the hard path, half of them were black. So in the case without the wall, when the electrons exit as 100% white, they could not have taken the hard path, because if they did, half of them would be black. Did the electron take the soft path? No. By the same reasoning, if I block the hard path, so all of the electrons take the soft path, half of them end up as black. Therefore, in the experiment with no wall, the electrons cannot have taken the soft path. Did the electron take both paths? Well, no, because when I put in the wall, we can always measure how many electrons come out at the end, and it's always the same as the number of ones that we feed in that goes through the unblocked path. So if you block a path, the electron always takes the other one. That means the electron always takes one path or the other, but not both. Right? We can always show it goes through one of the 2 paths by blocking one of them. Did the electron take neither path? No, It didn't take some other path or do something else, because if we block both walls, no electrons reach the end. It removes all output. So it didn't do one, it didn't do the other, it didn't do both, and it didn't do neither. This seems to exhaust all logical possibilities. So what could have possibly happened? Well, I'll tell you the answer. What happened is that you should not use natural language to try to reason about things in this way, because this is not a mutually exclusive set of four possibilities. There's a new possibility that we just didn't have a word for before, so we invented a new word. What happened is that the electron took a superposition of the two paths. So what happened is that the state of the system, the ket electron, was in a sum, 1 over root 2 times hard path plus soft path. Now let me be clear. When I add together two vectors, I am not saying the electron took both paths. It's not taking both paths, right? When we measure it, it's always in one or the other. So this is a new and previously unknown logical possibility. Things don't have to do one thing or the other or both or neither. They can do a superposition. And this is the reason, coming back to Greg's question at the very beginning, why is it natural to assume that the state of a physical system lives in a vector space, which means you can add them? It was not natural when I told you that to begin with, but now that I've explained to you this experiment, I'm hoping you're starting to believe it is a necessary ingredient, right? Because we are required by this experiment to consider a state which is a sum of two different states, which is not literally doing both of them, but which is in some sense a superposition of those two. And that's what the addition in the Hilbert space of quantum states represents. So we need to be able to add vectors because they do things like this, these strange combinations, which allow possibilities like measuring 100% white in the third experiment, which we would not expect classically. So just to put a final nail in the coffin, as I said, if we put a wall in either of the paths or install cameras to check which of the paths the electron goes down, it collapses based on fact 5 I told you. If you measure it, it collapses a superposition to one or the other. But if we don't measure which path the electron takes, it remains in a superposition, and this superposition happens to be an eigenstate of the color operator with eigenvalue white. So that's why this is 100% white, because it's in an eigenstate of that color operator. Now I'm going over, so I won't do the exercises, but I might actually write up a little homework for people who want to think about this before the next version, the next iteration of this talk. And in that homework, you can go through explicit examples of the matrices for hardness, which look like this, and the matrix for color, which looks like this. And you can see that all of the experiments I just described very naturally fit into this framework that we have been developing. So that, for instance, the superposition that I just had on the previous slide corresponds to an eigenvector of this matrix with eigenvalue white. Well, actually, I think the one that I wrote is black, but the labels are kind of irrelevant. I'm just calling them black and white. But it's an eigenvector of this matrix, and you can check that if you use these matrices and do just linear algebra, then all of the results of those experiments come out in the way that you would expect. So I'll skip the exercises for the point of time, but just to end this act, and then I'll just have one or two slides to tell you what I'm doing next time. But the punchline of this whole discussion is that measuring a property of the electron changes its state, and when we measure color and get black, the electron collapses to a new state. In that new state, it does not have definite hardness. And that's the fundamental reason for all of the experiments that we just saw. So you can never have an electron that simultaneously has definite color and hardness, because there is no vector that is an eigenstate of the two matrices associated with those properties. So another philosophical point. When people say you can't simultaneously know color and hardness, this is not a technical obstruction. It's not that, oh, it has a color and hardness, but it's just very difficult, so we can't know both. You just know one or the other, just because it's hard. Not hard as in hard electron, hard as in difficult. That is not the case. It's not a tree falls in the forest question where, no one was there, so we don't know whether it made a sound or not. It's worse than that. I claim that a hard electron an electron in that state has the property that it does not even make sense to speak about its color. It's just not a property that exists, because an electron in that state is not an eigenvector of the color operator. So it's not just, oh, it's hard to know both at the same time. It's, in fact, the sequence of words, what is the color of a hard electron, does not even make sense. It's not even a valid question to ask. It doesn't have that property. That's part of the weirdness of quantum mechanics. Okay, that's it for the talk. It's been just about 2 hours and a little more. So I'll do the last 2 slides and then take questions and release you, since I've occupied 2 hours of your life. So we've learned a lot of quantum mechanics, a great deal of quantum mechanics focusing on Hilbert space and Hermitian operators. But all of this has been for one Hilbert space. As it turns out, even though I motivated this whole talk with entanglement, we can't understand entanglement with the stuff I've told you so far, because to understand that, we need to think about Hilbert spaces like this, where O times is the tensor product. And in fact, the definition of entanglement I'll tell you next time is that a state in a tensor product Hilbert space is entangled if it cannot be written as a tensor product of states in the 2 individual Hilbert spaces. So in fact, it's entangled if it does not factorize as a tensor product. So I can't explain that at the moment because I'm way over time. So instead, I'll say one other interesting fact we have not discussed. You might think that an ensemble of 100 particles that are all in this superposition state, superposition of being 0 and 1, you might think that's kind of similar to an ensemble of states, half of which are in the 0 and half of which are in the 1 state. Right? Because this is like, somehow it's half 0 and half 1, so that's similar to being in a bucket where half of your electrons are 0 and half of them are 1. That is not true. Those two things are not only not the same, they are not even close. They are extremely different. To have an ensemble of all of your electrons being like this versus an ensemble where half are 0 or half are 1. Very different. The first is a pure state and the latter is a mixed state. And in the next talk, I'm hoping I will explain to you how entanglement on a bipartite Hilbert space gives rise to these so-called mixed states on the 2 tensor product factors. And finally, the von Neumann entropy, which we talked about in the 3rd vignette in the very beginning. The von Neumann entropy is a particular quantity you can measure for these mixed states that characterizes the entanglement of the parent pure state. And once I've told you that, then we will have begun really the proper beginning of quantum information. That's where the subject starts in earnest. Okay, thank you for your very long 2 hours of attention, and now I'll stop the recording and we can discuss, or you can leave if you're tired.